Hello everyone. Today I'm gonna talk about the digits of numbers. So first, let's denote an minus 1 until a2, a1, a0. This as the digit decimal representation of a positive integer n. Then let's denote LK of n. For example, if k equals to 4, then this means the last 4 digits of this integer n. So let LKN be the last k numbers of this integer n. Then LKN equals to ak minus 1 until a0. Then we have n, which is this part, n equals to 10 to the k times an minus 1 until ak plus lkn. So let's see an example. So if we have an integer 98765431, then that's a0, a1, a2, a3, a4. Well, this is a0 and this is a1. So if we want to find the last 4 of number n, then L4 of this number n is equals to ak minus 1. So 4 minus 1 is a3. So that's a1, that's a2, that's a3. We have L4 equals to 4321. Thus, we have the number 9876544321 equals to 10 to the 4th times 98765 plus 4321. And this is true because that will equals to 987650000. And if we add 4321 on it, it will become this number n. So another property is that if we want to find the remainder of, for example, this n upon division of 10 to the k, we have the remainder equals to LKN. So if we divide 987654321 by 10 to the 4th, we have some number right here, and left with the remainder of 4321. Thus, this is basically the notions in digits. Now let's look at some questions. So for the first question, I just wanted to remind you that while we solve for digit problems, don't forget to use like Fermat's theorem or Euler's theorem to solve more quickly. So you can use Euler's theorem. So phi, well, we find the last digits. We use phi of 10, which equals to 4, and 3 to the 4 is congruent to 1 mod 10. Thus, 3 to the 1000 is congruent to 1 mod 10. We have 3 to the 1003 is congruent to 27, which is congruent to 7 mod 10. Thus, the first answer is 7. For the next one, we find the last 3 digits. We have phi of 1000 equals to 400, and 1003 to some power, which is also congruent to 3 to the 2002 to the 1001, and we have 3 to the 400 is congruent to 1 mod 10. Thus, 3 to the 2000 is congruent to 1 mod 10, and 3 to the 2002 is congruent to 9 mod 10. Thus, this is congruent to 9 to the 1001 power. For 9 to the 1001 power, we have 9 to the 1000 is congruent to 9 mod 1000. This is Fermat's little theorem. Then we times 9. On both sides, we get 81 mod 1000. Thus, the answer for question 2 is 81. Now for the next question. In how many zero can an equals to 1 to the n plus 2 to the n plus 3 to the n plus 4 to the n for natural number n? So first we can check when n equals to 1. We have 1 plus 2 plus 3 plus 4 equals to 10. So at least one zero can this number n. Now if n is bigger than or equal to 2, and let's test if that L2 of an equals to 0, which means the last two digits is 0. If the last two digits is 0, then we know that this number is divisible by 100. Then 4 divides an. Thus, let's check 4. If 1n plus 2n plus 3n plus 4n is under the modulo of 4, we have if n is bigger than or equal to 2, then 2 to the n must divide 4, and 4 to the n must divide 4. Thus, this is congruent to 1n plus 3n. And 1n is always 1 because n is a natural number. Thus, this is congruent to 1 plus 3n mod 4. For this, we have 3n is congruent to negative 1 mod 4. So while we check n, we have, if when n equals to 3, we have 3 cubed, which equals to 27, minus 1, which is plus 1. And this is 28, and this is 28 is divisible by 4. Thus, 1 cube plus 2 cube plus 3 cube plus 4 cube. We have 1 plus 8 plus 27 plus 64. This equals to 9, and that's 36, and that's 100. So n, when n equals to 3, we might end with 2 zeros. Now, let's try to check if n is bigger than or equal to 3, and L3 of an equals 0. So, as usual, you know that 1000 will divide an, thus 8 divides an. So let's look at 1 to the n plus 2 to the n plus 3 to the n plus 4 to the n under the modulo of 8. So if n is bigger than 3, then this is divisible by 8 and this is divisible by 8. As usual, we can eliminate these two, and thus an is congruent to 1 plus 3n mod 8. Therefore, 3n is congruent to negative 1 mod 8. But is this possible? So let's look at 3 under the modulo 8. 3 to the first power is congruent to 3 mod 8, and 3 squared is congruent to 1 mod 8. 3 cubed is congruent to 3 mod 8, and 3 to the fourth power is congruent to 1 mod 8. Thus, 3 to the n is congruent to negative 1 mod 8, it will never happen. Thus, the most zero that an can n is 2. And yeah, the question is solved. Now let's look at the last problem. Determine the least positive integer n with the following properties. First, the last digit is 6, and if delete the last digit and place it at the leftmost of n, you have a number 4 times as large as n. So first let's denote n1 having the digits of ak minus 1, all the way to a1, 6, and n2 having the digits of ak minus 1, all the way to a1. As the question suggested, if we put 6 at the leftmost of n1, then 6 ak all the way to a1 equals to 4 times as large as n1, which is 4 n1. And we can simplify this as 6 times 10 to the k plus n2, and this equals to 4 n1. And we can keep simplifying, thus n2 equals to 4 n1 minus 6 times 10 to the k, which equals to 4 times. So for n1 equals to n2. For n1 equals to n2 times 10 plus 6. So we can substitute n1 by n2 times 10 plus 6. 4 times 10 n2 plus 6 minus 6 times 10 to the k. Thus, n2 equals to 40, n2 plus 24 minus 6 times 10 to the k. And we have 39, n2 equals to 6 times 10 to the k minus 24. By dividing 39 on both sides, we have 6 times 10 to the k minus 4 over 39. And we can simplify this as 3 and 13 equals to n2. Now let's look at n2. n2 is thus equals to 3 times 10 to the k minus 4 over 13. You know that n2 is an integer and 3 is an integer, thus this must be an integer, and we can find k in order to find n2. Thus, we have a property for k, thus, which is 10 to the k is congruent to 4 mod 13. So let's try to add numbers of k. First, 10 to the first power is congruent to 10 mod 13. And 10 squared is congruent to 9 mod 13. 10 cubed is congruent to -1 mod 13. Thus, when we times 10 squared by 10 cubed, we have 10 squared times 10 cubed is congruent to 9 times -1, which is -9. And -9 is congruent to 4 mod 13. Thus, we have 10 to the 5th power is congruent to 4 mod 13. We can try to solve 10 to the 4th, but 10 to the 4th does not congruent to 4 mod 13. Thus, 5 is the least k in this question. Therefore, we have k equals to 4, k equals to 5, and n2 is thus equals to 3 times 10 to the 5th minus 4 over 13, which equals to 15384. Thus, n1 equals to 15384.6, and we solve the question.